All right, hey everybody, Mr. Judson here. Hey, just real quick, one of the things that I need for people to do is to in that little file that has Judson's videos. When you go to get those links, make sure you read the first part. That's where I'm kind of putting my daily messages. Things that we need to pay attention to, things like that. One thing that's important is I really want you guys, as you're watching the YouTube video, either click on the thumbs up or the thumbs down. Thumbs up means it makes sense to me, I understand what you're trying to say. Thumbs down means I don't understand. I don't know what's going on. And I really need that feedback because I need to know if what we're doing is working for you guys. And if it's not, I got to figure out a way to adjust. So if you could do that for me, that would be really helpful. All right, so the next thing that we want to look at is the idea, and I'm looking at my book here on page 459. If I take a region between two curves and I rotate that around a line, then what I'm going to get is a shape that's hollow on the inside. When you look at this, you can see that this straight edge is this straight edge right here, but inside this figure we have a little bit of a curve. And so it's almost like there's a funnel inside of this shape. And that funnel is not part of the volume because that's something that's missing. Well, if we think about our disk method, let me just draw a disk right here. So it would look like this, and that would be solid all the way around. Well, now what we're saying is we don't want all of this. I want to get rid of a small part. So maybe what I have is this cylinder in the middle that we're not counting. It's almost like if we could just say it's like a washer. Like if you got nuts and bolts and there's a washer. And that's what we call this. We call it the washer method because it's not solid all the way through. We want to subtract off the part that's missing. And so, last time on Thursday we talked about the disk method. Today we're going to talk about the washer method. And if you can see this picture right here, it looks like a washer. What we want to remember is this is a very little thickness. It's very thin, just like our rectangles when we were trying to find the area underneath a curve. This is a very small amount. Since it runs in the x direction, we would call that dx. And I would set this up just like I would for the disk method. It's just we're doing washers instead, and we don't want the middle part. So what I'm going to end up doing is a larger cylinder minus a smaller cylinder. If I write that out, we'll say pi r squared times dx. So that's my circle times the thickness minus pi r squared dx. And what I'm doing here is I'm thinking that the capital R is the big radius. We've got our axis of rotation. This would be the line that we're rotating our curve around. And so our big radius would be the distance from that line that we're rotating around up to the edge of the curve. And then the little radius, little r, would be from that line that we're rotating around to the part that's missing. So if we could look at this part of the drawing right here, see how they use a capital R? This is our axis of rotation, and we're going to the outer curve. And then the part that's on the inside, that would be the little radius, that's the smaller one. And when you do that, when you subtract these, you get the area that's left over, which is the part of the washer that's solid. Well, just like before, this is, we're going to add up a whole bunch of these, so this is just an integral from a to b. And since they both have a pi in them, I could factor that pi out times the integral a to b. And then I've got large radius squared minus little radius squared, and I'll factor a dx out of each of those. And this right here is our formula for the volume if we have a hollow piece. Small radius is the part that's missing. The large radius is the outermost part of this solid figure. Here's another example right here. If I took a square root of x function and a parabola, and I took the area between those two and I rotated around the x-axis, I would get this shape right here. And again, it looks like a bowl, but on the inside it almost looks like a funnel. Make sure you're looking at this picture on your book because it may be hard to see here. If you guys take a look at it, that might make this a little bit easier. So we'll go ahead and start with this problem and try to find the volume of the solid figure that's left. It's a bowl with an inside to it. It's hollow, but that hollow part is more like a funnel than it is the inside of a normal bowl. Let's go ahead and try that. Alright, so this problem is on page 459. It's example number 3. And what they're asking us to do is to rotate the area between y equals the square root of x and y equals x squared about the x-axis, and then find the volume of this solid. So when we say area between, that's the first thing we looked at when we started this distance learning. Area between two curves. And now what we're doing is we're adding to that. I'm going to take that area and rotate it around the x-axis and try to find that volume. So if I was to graph y equals the square root of x, that would be a curve that goes like this. If I graph y equals x squared, that's a parabola. But the part that I'm interested in is just this area between these two curves right here. So I'm going to go back and erase part of this. I really don't need the parabola on this side. And let's see, I suppose I got to get that tick mark in the right spot. It should be right here. So these two graphs would intersect at 1, 1. If we set those two equations equal to each other and solved, that's what we'd find. They intersect at 0, 0 and 1, 1. And so what we're doing is we're taking this area right here between the two curves and we're going to rotate that around the x-axis or about the x-axis. And so once I do that, I'm going to get a shape that looks like this. So here's the square root getting rotated. Here's the parabola getting rotated. There would be, I guess, the opening to this bowl, this hollowed out piece. And I wouldn't really see this part, so I'm going to make this a dotted line. Same thing here. And so there's what this shape would look like. I've got this thing that was rotated around the x-axis. It's hollow on the inside. It's kind of a funnel type shape that's sideways. And it looks like a bowl on the outside. So what I want to do is, we're calling this the washer method. And so what I want to do is I want to draw something that looks like a washer. So if I was just finding the volume and it was solid, this is what I would draw, and this would be my disk for the disk method. That's the last thing we did. But this piece is going to be hollow right there in the middle. So when I set up my integral, I'm still looking at this thickness right here, and I'm saying that runs left and right, same direction as the x-axis. So that means I want this thickness to be dx, a small x value. And that means everything in my integral has to be in terms of x. So our formula, we had pi on the outside. I had big R squared minus little r squared on the inside. And then my integral went from a to b. So again, when we say from a to b, that means as you stack these washers side by side, this is going to be a very small washer here, and we'll have a larger one down at this end. But as I stack those side by side, they go from what x value to what x value. And that should be 0 to 1. So that's what I have on my integral. We're starting with our first washer at x equals 0. The last one is right here at x equals 1. We know that this is 1 because that's where these two equations intersect. So now what I need to do is I need to come up with an expression for the large radius. So the large radius, and this is going to get a little messy, but I'll do the best I can. It starts right here. This is my axis of rotation, and it goes up to this curve right here. Okay, so there's big R. And so really that's just a y value. We're going from the x-axis up to some point. It's the y-coordinate of wherever we're at as we inch our way from 0 to 1. So if this is just a y-coordinate, I want to ask myself, okay, this equation right here, that one came from y equals the square root of x. And I need everything in terms of x. So if the y-coordinate is the radius and y is equal to the square root of x, that means that's my large radius. So I want the square root of x squared. Let me just go ahead and say that again. Okay, the radius starts here and it goes to the outermost curve. And the radius is just that y distance right here. But we're saying that y is equal to the square root of x. So if the radius is y and y is equal to the square root of x, I'm going to put that square root of x here and then square it. That's my big radius squared. And now I want to subtract the little radius squared. Well, now I got to look somewhere else. Now I'm looking at from the x-axis up to the dotted curve. That's the little radius. And so the dotted curve is the parabola. My radius is equal to a y-coordinate, but y is equal to x squared. And so my little radius would be x squared, and I have to square that. And then integrate the whole thing with respect to x. So again, from the perspective of the integral, that integral isn't very hard. The hard part is getting it set up and understanding the picture. At this point, I've got pi times the integral 0 to 1, square root of x squared, that's just x. X squared squared, that's just x to the fourth. And I can solve that integral without a whole lot of effort. So we got pi times x squared over 2 minus x to the fifth over 5. We're going to evaluate that from 0 to 1. So if I plug a 1 in first, I get pi times 1/2 minus 1/5 minus what I get when I plug in a 0. That would just be 0. And so let's see, if I convert that to tenths, that would be 5/10 minus 2/10. That would be 3/10. So my final answer is 3 pi over 10 cubic units. This might be one that you would want to rewind and watch it again, and maybe a third time, maybe a fourth time. I think the more you see it, the more you start to realize exactly where everything came from, and it makes a little more sense to you. So go ahead and do that as many times as you need to. All right, so here's a problem for you guys to try. First, I think before you even start to set up the integral, we want to graph these two equations on the interval 0 to 2 and at least see what we're working with. So you guys go ahead and do that, then we'll read through the question. All right, so here's the graph that I get. I've got a parabola that's been shifted up 1 unit. So that's going to look something like this. And then I've got the line y equals 1, which is just a horizontal line like this. And we're going from 0 to 2. So we're taking this area right here and rotating that about the x-axis. So if I did that, I would have another piece kind of sort of like this. We'd have this hollow part in the middle here. And it gets really hard to draw this as a nice three-dimensional picture to understand. So at this point I kind of stop and I just try to imagine in my head, okay, if I rotate that around, yeah, I've got something that's sort of like a funnel looking shape, and what's missing in the middle is like a cylinder. It's hollowed out. It's almost like you drilled a hole through with some kind of drill bit. Okay, so it is hollow. That anytime it's hollow, that always says to me washer method, large radius squared minus little radius squared. All right, so I want to draw a picture of what that washer would look like, and it would look something like this. And the part that's hollowed out in the middle would be right there. So again, here's our thickness. It's running left and right, same direction as the x-axis, so we're going to call that dx. And it means I'm going to stack a whole bunch of washers side by side like this. And so as I do that, they're going to start at x equals 0 and go all the way up to x equals 2. So as I start to write my integral, I've got the integral from 0 to 2. I've got pi times big radius squared minus little radius squared dx. You guys see if you can complete that integral. All right, so my big radius, it starts right here on the line that we're rotating around, which is the x-axis. It goes up to the top curve, which the top curve is the parabola. This right here is just a y-coordinate, right? From the x-axis up to here, that's just a y distance. And y is equal to x squared plus 1. And we want this whole thing in terms of x. So my integral now becomes pi times the integral from 0 to 2 of x squared plus 1, and I'm going to have to square that, minus little radius squared, and then dx. So my little radius goes from our axis of rotation, again that's what we're rotating around, up to this line right here. And what you notice this time is as we move across, starting at 0 and going all the way to 2, that inside radius never changes. It's always exactly 1 unit. And when that happens, we can just say 1 squared. See, here I need my x variable because the radius is changing. Even though it's the y-coordinate that's changing, we're saying y is equal to x squared plus 1. So whatever this is, it represents that larger radius. All right, now we have an integral to solve. I'm going to go ahead and square this, so I'm going to get pi times the integral from 0 to 2. Square the first term, you get x to the 4th. Multiply the 2 and double it, you get 2x squared plus 1, and then minus 1 dx. So I guess if I'm going to add 1 and then subtract 1, I can go ahead and just get rid of that. And we'll call it that right there. So that's an integral that I don't think I need my calculator for. X to the 5th over 5 plus 2x cubed over 3 We're going to evaluate that from 0 to 2, and then multiply it by pi. So let's see, I'm going to get pi times, if I plug in a 2 to the 5th power, that's 32 over 5. Plus, if I put a 2 in here, I get 8 times 2 is 16 thirds. Minus what I get when I plug in a 0, which would be 0 again. So I just need to add these two fractions right here. I'll do that on the calculator. So I got 32 fifths plus 16 thirds, and I got 176 fifteenths. So my final answer is 176 pi over 15 cubic units. There's our answer. Let's try another one. All right, so let's see. We're going to rotate the area bounded by y equals the square root of x. Bounded by means these are the boundaries. Y equals square root of x, y equals 0, and x equals 4, about the line x equals 6. Oh boy, that's something different. Well, let's not worry about this yet. Let's just get a picture of the area that's bounded by these three things, and then we'll take care of that. So let's see, I've got y equals the square root of x. That's a curve that looks like this. Y equals 0 is a line right here at y equals 0. So that's really just the x-axis. And if I go out to 4, that means that this curve should go up to that point right there. So I'm going to take this area right here, inside of this curve, and I'm going to rotate it about this line right here. This is the line x equals 6. So yeah, this is different. We're not going around the x or the y axis this time, but this is going to happen, and so we need to figure out how to deal with this. So if I take this picture and I rotate it around like this, that means I'm going to get this exact same shape over here on this side. So let me just draw a quick picture of that. Let's see, 2 units in, we've got a straight line that goes up to here, and it's going to go 4 more units, 1, 2, 3, 4, and we're going to have a curve that goes like that. So if I rotate this around, it almost looks like, it's not a very good one, but a bundt cake pan. If your parents have one of those, it's hollow in the middle. You know, usually they're kind of curved here, but okay, this one's a little weird. And so you kind of have to picture that. It's almost like a donut going around, but it's a donut that somebody pushed a cookie cutter through. It just got kind of cut in the middle. So if I rotate this around, you know, we have to picture our washer as looking something like this. And it's hollow in the middle. So remember, we're going to stack these washers on top of each other. The biggest one will be down at the bottom, and the smallest one will be up at the top. But the part that's cut out in the middle, it's always the same. It's not changing size. That's important for us to notice. So right here, I would look at the thickness of this. This thickness is running up and down. That's in the y direction. So I'm going to want everything to be in terms of y. All right, so far this is what I know. I've got an integral in terms of y, and I've got a big radius squared minus a little radius squared. There's going to be a pi out in front because that's our formula. And I've got to figure out, these washers are going to stack from what to what. I've got to think in terms of y values. So, if these stack like this, it means they start off at y equals 0, and they're going up to, let's see, whatever we get right here. So if I take 4 and plug it back in, I get y equals the square root of 4, which is 2. So our top washer is going to be at y equals 2. So we could say our integral is going to go from 0 to 2. Now again, I know that this stuff is a little difficult. It would be nice if we were together and we could ask questions. I really think this is one that you're going to want to watch over and over again. And each time you watch it, hopefully you pick up something that you missed maybe the first time. All right, so now I just need an expression for my large radius. So every problem we've done so far has always gone from either the y-axis to some point or the x-axis to some point. Well, here, my large radius is going to look like this. It starts at this line right here and goes back to this curve, which was the square root. Now, if you remember this, let me just draw something here real quick. If I had a number line and I said, how far is it from 27 up to 62? What's this distance right here? You would just go, well, 62 minus 27. Right? What would that be? That would be 35 units. That's how far it is from here to here. And what we did is we took the larger value minus the smaller value. So I want to figure out how long this segment is, and I really should do the same thing. I should take the larger value minus the smaller value. Well, since we're rotating around this line that's always at x equals 6, 6 is the larger value. I don't know what this is because as this radius moves to different points, this x value is going to change. So I need to call this large radius 6 minus whatever that x coordinate is. That's the radius. 6 minus x. Now there's a bit of a problem here because I want everything in terms of y. I don't want x variables here, but I'll figure that out in a minute. All right, my small radius, that's going to go from our axis of rotation to this inside edge of our donut or bundt cake pan, whatever we're calling this thing. That's my little radius. And in this case, no matter what, it's always going from 4 to 6. Right? So 6 minus 4, that means it's 2. Since there's no curve here, it's just straight up and down, that radius never changes. It's always going to be 2. Now, let me just say something that's really important here. When you're trying to figure out these two radii, I don't want to draw the picture over here because this wasn't the original curve. This is a result of rotating this around the line x equals 6. I always want to make sure I'm drawing my radius from the axis of rotation back to the original curve. Really important. All right, I still have to fix one thing. I got to get this in terms of y. Well, the equation for this curve right here was y equals the square root of x. So if I go over here and just say, okay, y equals the square root of x, and I want to know what x is equal to, I'll square both sides. And so now what I could do is I could put y squared in place of this x. So my integral now looks like this. I've got pi times the integral from 0 to 2 of 6 minus y squared, and I have to square that. I'll go ahead and just do this right now. Minus 4 dy. And now I've got an integral to solve. And again, you can punch this in the calculator if you want, or you can work it out by hand. I think the more we do by hand, the more we remind ourselves of how to do these things, and I think that's important. Is just staying sharp and making sure we don't forget anything. So pi times the integral from 0 to 2. Square the first term, you get 36. Multiply the 2 and double it, that would be a negative 6y squared. Double that, you get a negative 12y squared. And then you square the last term and you get a positive y to the 4th, minus 4. So so I have enough space here, I'm just going to say 36 minus 4, that's 32. And now I'll go ahead and integrate that. So I'm going to get 32y minus 12y to the 3rd over 3. That'll become 4y to the 3rd plus y to the 5th over 5. We're going to evaluate that from 0 to 2 and then multiply it by pi. I'm going to run out of space here, so I'm just going to write down the final answer so we know what it is, and then you guys can check that. Alright, so there's my final answer, 192 pi over 5 cubic units. You guys, I really can't tell you how important this is, this idea of watching this video over and over again until you feel comfortable with it. Most people don't get that opportunity. You hear it once in class and it's like, what did he say when you get home? Now we get to rewind, pause, stuff like that, and take advantage of that. Use that as a way to help you understand as opposed to getting frustrated. Okay? As always, email me your questions. I would be happy to answer those. The more you tell me, the more I know about what's going on. All right, well, that's what we have for today. Here's our assignment. So this is now assignment number C3, page 463. We're going to do 5, 6, 13, and 14. All right, you guys, stay safe. Don't forget, thumbs up, thumbs down if you understand. And also, if you do a thumbs down, let me know. Send me an email. Tell me what part you don't understand, and I'll do the best I can to help. Also, make sure you're always reading what's in that file, that has all Judson's video links in it. The stuff up at the top is changing each time I upload videos, and so any new information I have, I'll put on there. All right, we'll see you on Thursday.